I guess with that, Ken, we can hand it off to you.
Cool. All right, welcome everybody. My name's Ken. I work with Adam in the ARM program. I just wanted to turn my camera on to say hi, but otherwise I'll turn it off for the rest of this. It'll save bandwidth and make my computer freak out less. Maybe. All right, there we go. Cool, thank you. I'll let Adam interrupt me when there's a question, but otherwise, yeah, feel free or just go ahead and speak and we'll do that right away. So what I'm going to do is I'm going to show off the Python notebook, but I'm actually running it locally, so it might look a little bit different than what you see. But essentially, it is exactly the same code. I'm just running it locally. So what I'm going to do is I'm going to go into the scientific libraries. There's 3 of them here, and one of them is called Numpy. We're going to start off with Numpy. So when we first started looking into this, we thought we were going to do an intro to Python, but I think that is covered elsewhere on the internet. There are a number of resources out there that can do a probably better job than I can with that. There's a very good wealth of information on that, but in reality, you're here more for the scientific computing. So we're going to focus on the 3 that I was thinking were the most important libraries that help you just to get going, get you enough to be dangerous and start working on some actual data. And so that's what we're going to try and work through here. So what we're going to do is start with Numpy. You've seen a little bit, I think, already about what it is, but the one thing I want you to think about Numpy is basically in addition to the Python code, but it's kind of important to think about it as a different space. So there's things that are available in the NumPy space that are not available in the Python space. Most of the stuff will translate back and forth very well, but sometimes the Python stuff running on the NumPy stuff doesn't give the right answer, or doesn't give the answer you expect. And so it's better to operate in that space. So for example, if we run through this first one here, you'll see that Python has different types. We have an integer, we have a float, and we have a string. And so when I print out the type, which is what I'm doing here, you'll see that it comes out as integer, float, and string. The reason that NumPy exists is that it needs to help fill in the gap between essentially the space where Python is into a space more similar to maybe if you programmed in C or Fortran, that it has different data types. So for here example, we have the different types at 8, 16, 32, and 64 integers. And the same thing with floats, you have 16, 32, and 64. And so when I print these out, you'll see that it says it's a NumPy float, and then the type of float it is. There's other types in here, including Booleans. And if you just want to have it say, well, give me any sort of, give me the default integer, it would just be integer underscore or float underscore be the default. And there's other types that we're not going to go to today, but you may need, including unsigned integers, complex. And then it also has the same string arrays. And you'll see that it actually comes out when it prints it, it comes out as U11, which is the Unicode. So these are important because what we're going to do is we're going to work with NumPy arrays, which is similar to a list in concept, but actually quite different. So right here, what we're doing is we're creating a Python list, and then I'm taking the same numbers and putting it into a Python array. And then we're going to print the types out here. So you see the first one is a list, and the second one comes out as a NumPy ND array. N means n-dimensional array, so you can have more than one dimension. And you'll see that when I do type B, it's not giving me the types that we had before of integer and float. It's just telling me that it's a NumPy array. If I really want to know what is typed inside of it, I have to pull out one element, in this case, the first one, and then it's telling me it's an integer 64. But the better way to go about this is not to operate in the Python space. This is the Python area. It's better to go into NumPy space. So now we have this method, which is dtype. And so that'll actually say, because this is a NumPy ND array, go down into it, figure out what it is, and then tell me that information. And it says it's an integer 64. So one of the reasons that you would really want to use Python is the performance. I'm going to run a couple cells here to get them going. So what we're doing here is this time it thing is going to run it a bunch of times and then give us an answer. But I've got 100,000 values. You can think about a list of 100,000 elements. Range is a Python thing that goes from 0 to some number, and then turning it into a list because range is a iterator. And then I'm going to loop over it, and I'm going to add 1 to every single value. And you see that it took 7.81 milliseconds, which is pretty fast. But we can go a lot faster if you start using the actual pre-compiled language, basically, which is NumPy. So you'll see it's the same number here, 100,000. And basically, I'm doing the same thing. I'm just using a range, which is going to do the same thing as the range above. And then I'm going to add 1 to every single element. But you notice that there's no for loop here. And that's probably the most important thing to remember about NumPy, is that it allows you to eliminate the need for a for loop. For a very large number of iterations, a for loop in Python is a very slow operation. And you can see here that it's 37 microseconds. So the speed is significantly faster. And that's one of the main reasons that you're going to probably want to use NumPy. Well, the nice things, though, is how well the two play together. So you see here that we can go and create a list to type list, and then we get the size of it using the length keyword here. And then we can just go ahead and convert that into a NumPy array just by saying NumPy array of the list we created above. And you'll see that it's already a NumPy array. And then we have these methods here that help us describe what's inside of it. So one of them is size, tells you the number of elements total, and one of them is shape. And so in this particular case, it's a one-dimensional, so we only have a one-dimensional. And you see this comes back as an integer, and this comes back as a tuple. And then what's really nice is that you can go back, and I can convert it back into a list very efficiently and very fast. So you have the ability to pop back and forth between these to work in either the most simple or the most efficient space, whatever works best for your programming. So first thing we're going to do here is we're going to go through and make some arrays. And the biggest thing that's different between arrays and a list is that an array in NumPy space is all the same type. In a list, they can be any objects. So here, we're going to do a NumPy array, and we're going to give it an iterator of 10. And you'll see that it comes back as these 10 numbers. We can also start that just in the NumPy by just doing a range. And you'll see it gives us the exact same values. Probably a little bit faster since it's actually running pure NumPy, not having to go Python and then change it into NumPy. And the nice thing is if you're familiar with list, you're going to understand how you're going to index into all of these. So here we have a range which says start at the value of 1, go to the value of 10, but don't include 10, count by 2, and you'll see we get 1, 3, 5, 7, and 9. Just like range would give us if we did the same operation. Same thing with counting backwards by -1. And then one thing you might want to think about before you go off and ever write your own little routines to do something is NumPy probably has a operation to do that for you already. So here NumPy has flip, which will go ahead and reverse the order. And the other thing that's really important to understand about the way the NumPy works, which is different than the Python, if you're used to IDL or MATLAB, it's this idea of broadcasting. So you don't have to do loops in order to do extraction or multiplication or operations between different variables. So here we've got A again, which is create above. We select just like we select in lists. So 0:5, we'll start at 0 and select up to 5, but not include the 5th one. And then if you leave it blank, it'll actually go and do everything to the end or everything to the start. You can go to the very end. So this is starting at the very beginning and goes to the end, but -1, but it doesn't include the last one. And then it's pretty forgiving. So our array is only size 10, but I said go to size 100, and it still works. And that may be awesome, or it may cause problems. It kind of depends on how you're programming.
Say, Ken, there is a question. Can you do non-contiguous elements? So I'm guessing like if you wanted to extract elements like 2, 4, 6, and 8 or something like that, right, Alicia?
Yeah.
Okay.
Yeah, so the way you go, I guess you could probably do I'd have to think about it. But there's another way you can do this where you create a Boolean array, and basically it's a true false. And so if you create that Boolean array to match your non-contiguous, you can plop that in and it'll extract it. The other way would be just to build an array of indexes that counts by 1. And so we kind of did that above with this. So you could create an indexed array, and then that is counting by 2. And then once you drop that index array into the actual A array, then it would come back as that. I think that's.
So is there no simple way just to, for example, have a list within so let's say there's no pattern to it. Let's say I want elements, 5 and 10. That's it.
Oh, yeah, you could just say, give me element 5 and 10.
What's the syntax for that?
Up here. So, see A. Here's a list. Not sure. I have to think about it. I don't know why it's not working.
It's just because 10 is not in the array. It's not a possible position. If you do 5 and 9, it's going to work.
Yep.
Oh, that could be it, yeah.
I just put one solution in the chat.
Yeah, that was it. So I created an Numpy array. I think you could just do
list. You just put a list within the argument.
Yeah.
Okay.
Yeah, that's all you gotta do.
Yep.
Okay. So one thing we can do is we can also work in multi-dimensional space by changing the shape of the array created a different way. So here I have an example of a 10 element array, and I wanted to do an A range. A range just starts at 0 and counts up to the number you want. But I didn't want it to be a 1-dimensional, I wanted it to be a 2-dimensional. And so we could reshape it by saying, make it a 2 by 5 or a 5 by 2, whatever works such that you can divide 10 into this shape. And when you do that, you then have this element, this array down here. And then when you print out the shape, you'll see that it's this tuple with the size of each dimension. And then the size comes back as the total number of elements. One thing to be careful about is if you were to do len, L-E-N, which is a Python function on this, it's not necessarily going to give you the correct answer. It's not going to give you size. It'll actually give you the size of the first dimension. So for example, if we did len on C, it would come back as 2, which is may not be what you're asking for. So that's where you kind of want to use the methods available for you in the Python space appropriately and not try and mix them too much. Or if you do mix them up, make sure you understand the results. And then the other thing that's really nice is that there's a lot of ways to create the arrays for you automatically, so you don't have to do any sort of iterations or special logic. For example, here I have the ability to do zeros, so multi-dimensional array of all zeros, multi-dimensional of all ones. I can set the type at creation time. And I can also use full to create an array of whatever shape I want set to a particular value. And then all of these all take the data type. You see here that we have a 2 by 2 array all set to the value of 7. We have a couple of other ones here which I thought might be interesting to know is that there's an index array, identity matrix, which is called I. And then there's a random function in there which will create your random values. And there's actually multiple different kind of distributions. It's not just a uniform distribution like this one is here. So probably the most important feature we talked about here is the broadcasting. So I just created an array of zeros, 20 of them, integer. And I just want to add 1 to it. So the syntax is just A plus 1. And you'll see that it added 1 to every single element. No loop was involved. But also notice that 1.0 0 here is a float. And in order for this to work, the only way that NumPy can execute this is to upcast the value from an integer, which is what a was over here when we created it, to a float. And that's pretty common. If you mix data types together, it's always going to choose the higher level. So it'll go up either to a float or up to a higher type of float. We can change it back, or we can say as type, so a as type, and it's going to change it back. It hasn't changed the value, it's just changed the type of it. And then when we want to subset it, we can subset it by saying, grab the values from 3 to 8, not including 8, add 10 to those. So this A here, this is not the full length of this array, this is a subset of it. Add 10 to it, and then assign it to these values. And as long as this is the same size as this, it doesn't have to be the same values with the same size, it can insert those values. You'll see here that we have all the original values, added 10 to a bunch of them, and then left the rest alone. You don't have to do it this way, but I wanted to show you this does exist. This is the shorthand way of doing the exact same thing above. In case you come across somebody else's code and you're wondering what's going on, this essentially is saying this part here is just duplicated twice in the code. And it's just a shorthand way by putting the plus in front of the equal sign. But this part here is exactly the same as this. So if you haven't messed around with not a number yet, I highly recommend you kind of get this concept wrapped in your head so that you understand it. It's really important for proper data analysis to understand the ability to not propagate a bad value through your data. The thing with this, though, is you have to understand how NaN works in order for you to use it properly. It's a recognized value in IEEE for many years now, so it's well established in the computing community. And you'll see here that if I print it out, it prints out, it looks like a string, but this is actually being interpreted by the print statement, and it's just printing NaN. It's a class float, which means you can't have an integer NaN, you can't have a Boolean NaN. And if you try, you either will upconvert or you will get an error. But the most important thing to remember is that everything that NaN touches, it taints. That means that if 11 plus NaN is always going to return a NaN, and any operation is going to return a NaN. So let's go take a look here and see what's going on. So in Python, the double equals is saying, is the one on the left equal to the one on the right, and return a Boolean of true or false. And so here we're saying the value of 1 is equal to the value of 1 and returns true. And so you think you could do the same thing with NaN, but you can't, because NaN is a special value inside the interpreter that it doesn't return true. So if you were to go look for it by saying, go find out where the value is equal to NaN, it's not going to return what you think it's going to do. In order to get this to work right, you got to use these special methods. And here's one, it's called isNaN. So it'll work on an individual NaN value or an array, and then that will return a true value, excuse me, a true value array, indicating it is a NaN. Also, what we're going to do with NumPy is we're going to go through and we're going to do a lot of operations. So for example, here is the min function, and on top of this array here, it's giving me the minimum value, which is 0. Now I'm going to add a NaN value into it. So you see the very first element here is NaN. And if we do the same thing, you notice that it comes back as a NaN. The reason this is happening is because think about what the mean is. The mean is adding values up and then dividing. So as soon as NaN touches every single value when it adds it up, everything in that array is turned to NaN, and you get a NaN. So the way you got to work with this is you got to give them a special method which says NaN mean, and this says if you bump into a NaN, just ignore it. And so now you'll see that it is able to perform the operation correctly. One other thing that's really important with NumPy is it has a concept of a time in a particular type. So if you're using anything other than this in Python, I highly recommend you learn about this and use it. It actually will become super helpful down the road. The basic one in the Python space is called datetime. So here's an example of how I get the date time right now. And that's going to be my time zone. I'm in the Mountain Time Zone. And if I wanted to get UTC, the method is just called UTC now instead. And you'll see that it comes back when it prints out as a date time, date time. If I wanted to do the same thing from a timestamp, so this is the number of seconds since epoch, there's a particular method for that. These all work one at a time. So this isn't going to work with broadcasting. So if you wanted to do a bunch of them, let's say you had 10,000 values, you have to do a loop. And we're always trying to avoid loops in Python wherever possible. So now we're going to go into the NumPy space, and we're going to do some of the same things. So for today, it just gives me a date, but you also see it comes back as something different. So it's MP date time 64 versus date time. That's pretty important to remember because that's the two different spaces you're operating in. Today is just a date, so you see it's just a date. If you want to get the time, the word is now. And so you'll see that it gives me the now. And you notice that this comes back in UTC. Bless you. If I then put in a time as a string, so you see you got the quotes here, this is actually a string, it'll interpret that and then put that into the date time. And you'll see when it prints it out in ISO format right here, which has the T in the middle. One thing to remember is that it remembers the precision that you put it in. So if I just gave it to the month and then said print it out, it remembers what precision I entered it. So it remembers to print it as the month. But if I give it the precision, which is the second value here, which is S, it then fills in the defaults for the rest of it. And that default can go down to a very low value. Nanoseconds, the one that works up to a point. If you go, there's actually lower precisions. It becomes a very short window of available times. So I didn't bother putting it in here. But there's a range of values all the way up from year down to nanosecond that work really well for atmospheric science data. But now you'd be saying like, okay, big whoop, you can do precision, who cares? It's really important when you want to start building things using the internal loops that Python has. So for example here, I'm saying start with this year and month and go to this year and month, but not including that month. And then I'm going to say do it as a day. And you'll see that we're using the same function we had previously of arange, and it automatically just goes ahead and fills in all those days because I set the date type. If I set this to a different date type, it's going to interpret that as the step and then create all the individual times. If we wanted to go and have the difference between two, we can just separate them. So here's two different date times I've created, and I'm subtracting the two. And what you'll notice is that it doesn't return a date time, returns something different called a time delta, because you can't have a difference in time be a time. And it'll tell you what it is, 366, and then the unit, which is day. That's really important when you actually want to add to a particular date time. So here we have a date time, and I want to add 12 hours to it. So I can then add 12 hours to this. You can actually just add numbers, but the nice thing is if you add time deltas, you get to pick the units. In that case, you don't actually have to set the data type for this.
Ken, so there's a question. Can we add time delta 64 as an array?
I believe that is true, yes. So you're saying you would want to not add the same time to every element of your time array, but you want to add different times to every element. Yeah, that should work in broadcasting as long as the two arrays are the same size. That's the most important thing about broadcasting is that the arrays have to work in array multiplications. So either there has to be the single value where it interprets to do it for all of them, or the number of values have to be equal so that the NumPy can understand how to actually broadcast along the dimensions. So I put this in at the end because I really want you to just know that it exists, but I don't think you need to memorize it. And this is how you get back and forth between the two spaces. So here we are in the datetime space, the Python space. And all you got to do is drop in your datetime into datetime 64, and it'll convert it into the NumPy space. It's a little more complicated to go backwards, depending on your opinion on what backwards is. So if I start off as a datetime 64, what I actually have to do is change the type to seconds, then change it from the space, which is date times 64 type, to an integer, and then take the number of seconds and then drop it in from UTC timestamps. This is basically epoch. And so now we're rolling it back into the date time space. So as far as NumPy goes, we just scratched the surface. There is significantly more out there, but I thought this was enough to get you understanding the core concepts of what is happening under the hood. But more importantly, just to get you excited so that you want to go look and see what else is available out there. I'm happy to answer questions. We're going to try to give you some more resources. There are plenty out there. And if you have any questions about where to find some good resources or how things are structured on the internet to find good answers, I'm also happy to help point you in that direction. So next, we're going to jump over into Pandas. I'm going to click on the Pandas IPython notebook. All right. So why would we not just live in the NumPy space? Sounds amazing. You can do everything in there, right? Well, what if you have more than one array and you kind of want to organize them together? That's where Pandas really excels. It's essentially an extension of NumPy, and it goes into a thing called a data frame. And I'm going to do my best to keep these terms straight. Hopefully you remember the terms because they really increase your ability to search on the web. So if you're talking about pandas, use the word pandas and use the word data frames, you come up with the answer quicker. A data frame, you can think about it like a spreadsheet, but that's where the comparison stops. It's much more powerful than any sort of spreadsheet you ever worked with. What we're going to do is we're going to import pandas. Convention is to import it as PD. And then we're going to create a data frame. So we start off here, we're going to create a dictionary. So this is the key and this is the values. And there's two of them, and we printed it out here. And then we're going to drop that dictionary into Pandas data frame. And you'll see that we created purchases here, which is a data frame. And the great thing is that Jupyter and Pandas play really well together, such that when it prints it out in this nice, beautiful way. You have the keywords on top, we're calling those columns. And then you have the rows with this index on the left here, which is automatically created for you, and then all the values. But in reality, Pandas is actually created from series. So here we have the type for purchases. You'll see that it comes back as a data frame. But if we just pull out this one column, this dot method here, and you'll see that it comes back as a series. So think about columns as series, and then the whole thing is a data frame. It has this idea of an index. Let's see if I can get both of them to be on the screen. If we run the same thing we did above, but this time we're going to tell exactly what the index is. And it doesn't have to be a number. So initially it was created as 0, 1, 2, 3, but in this case, they're strings. They could be times, they could be floats, they can be lots of different things. You'll see that it then puts a label on the row. So now I've labeled each row instead of having each row being this created index. If you print out the series, you'll see that it actually gives you those indexes and it tells you the type. So when you're printing, you're getting a lot more information. And that's one thing to remember though too, is that this right here is a series. It contains data values, which in the end is a Numpy array. But if you actually want to apply Numpy functions to this, you got to convert it into a Numpy function. May need to, sometimes it works, sometimes it doesn't. Convert it into a Numpy array first. But most of the time, we don't have to do that. Most of the time, Pandas will just solve the problems for us. If we wanted to get one particular row, then we can do two different methods here. One is called LOC, which is location, and that's looking for this index. And in my particular example, the indexes are strings, so I can then pass in a string. And it's going to just pull out that row, but it pulls it out for all the different columns, all this series. Let's say I don't know the name of the row, I just know the index of it. Now we're going to do this ILOC, index location. And now it's pulling out, you see the same value, and it pulls out the apples and oranges column names plus the values. But in reality, once you get to Pandas, you want to do one thing, and you want to do it really well, and that's read in some data. And if you're going to be reading in column data, this particular method is going to be your friend. Called read CSV. It allows you to pull in a file name, and I've created that above here, which is a path to a file name we have inside the notebook area. And it can be a relative or a direct path, a full path. And I can give it a bunch of keywords, which will solve a whole bunch of problems for me. In particular, I can tell it that the delimiter is this comma. I can tell it that the very first row in here is a header. So go ahead and grab those header values as my column values. I can tell it that I want to skip particular rows. And I can tell it that the first column is dates. Go ahead and parse those. So it's already done all this and does it very efficiently. You'll see that it's created a data frame that has the column rows. It's converted the time. It's actually a time stamp. It's not the time that's listed in the text file. It's created the indexes for me already. So if we use the Python space and we say len on data, you'll see that it returns 60. So this is a little bit difficult to understand because you're kind of guessing as to which dimension is it going to return. Is it the number of columns or is it the number of rows? So it gives me 60, which tells me that it's giving me the number of rows. But maybe the better way is to work in the Pandas space, where I could say the size is the rows times columns. The shape is really the information that I want. So you see the first number is number of rows and the second number is number of columns. And the nice thing is that NumPy and Pandas use the same words, shape and size. If I just want the first 5 rows, it looks just like NumPy, 0 to 5. So it goes from 0, not including 5, and then it pulls out the entire row. If I just want the columns, I do dot columns, and it pulls out the column names and returns them. It almost looks like a list, but it's not quite. You could wrap list around this and it'll convert it, but it's just a little bit different. Just so you understand that it is not exactly the same thing. But this is going to come back as an index object, and it does list all the different names. There's also a couple of methods already pre-built that may do what you need to inspect your data, so you don't actually have to write any code. So for here, data is my data frame, and .describe is this method that goes off and knows how to handle and do calculations of the most basic way to describe your data. Where count is the number of not missing or non-NaN values, but it's not giving the number of values total, because you can have a NaN value in there. And then your usual statistics for every variable in there. Or the correlation coefficients between each one for each variable. Or the covariance. And these are all pre-built for you, ready to go, and it works with all different data types. The other thing to look at is what is in this actual data frame. So here's my data frame. I'm saying go get this column, which is called timestamp. And then I'm saying go get the very first value in that. So this is a series. This is the first element in the series. When I print that type, you'll see it comes back as a Pandas timestamp. So it's close to the NumPy datetime 64 we just talked about, but it's slightly different. But you'll see that the data values are coming back as a NumPy float 64. So they are NumPy values inside the Pandas data frame. What that means is that we have a lot of the same methods available to us. So I'm going to extract the series, and then I'm going to say sum it up, or calculate the mean, or a whole bunch of other things I want to do on that. And it knows how to extract that column and return that value. And those are all Pandas-specific methods. We also have the ability to do the describe like we did above just on the series, so just that column. And the thing to remember, though, is that when you do extract this, it's not coming back as a Numpy array. It's coming back as a Pandas series, which for some operations is better because Pandas has different methods. And so maybe you don't want to leave the Pandas space. You want to stay in Pandas space. But if you did want to convert it into a Numpy array, you just wrap NP array around that, and it'll convert it automatically into a Numpy space. So one little tangent I want to go off on here. Pandas has two ways of extracting data from the Pandas data frame. You can either do it by a copy or a view. A copy is what it sounds like. You're taking a copy and you can mess with it. It doesn't affect the original. A view is basically pointing back to the original data. So if you're messing with the view, you're messing with the original data. It just depends on what you want. If you want to mess with the original data, then go ahead and do a view. But if that's not what you want, then go ahead and throw a dot copy on the end of your extraction, and then you don't have to worry about it. And in fact, I'd recommend doing that just in general, just because it's explicit as to what you're working with. The other thing that's really nice about Pandas is that it has the ability to do analysis on your data in a more larger suite of functions that are available to you than just the NumPy. So for example, I can create a NumPy rolling mean, boxcar mean, by giving it the size of my boxcar using this rolling method. And then this is telling the rolling method what to do with that subsection. And you'll see that it rolls through and creates a value, rolling mean all the way through. But because it needs to pick the first previous 9 values, and there isn't any at the start of the array, it fills that with nans, and then nan taints that entire mean, and you end up with nans for the first 9 values. So the way we can tell it not to do that is be a little more specific in how we want the calculation to be performed. So the only thing I've done now is I said the minimum number of periods, the minimum number of samples that must be a real value is 1. Then go ahead and perform that operation, in this case, the mean, and you'll see that it comes back with a value. If we want to set a particular value to NumPy nan, because it's bad data or whatever you want to call it, we can do that the same way we're doing in NumPy space. And then you'll see that it actually has set those values in that series to nans. And then we can perform that operation. And the thing that we can also do is take all these same methods that we were just applying to the series and apply them to the data frame. So we're doing the exact same thing here. We're applying the max method on top of the rolling method. And the end result is it happens on top of the entire data frame, not just the series. So this is also just the tip of the iceberg of Pandas. Very, very powerful for one-dimensional data. But when you get into multi-dimensional data, it's not as awesome. You need a different model to store n-dimensional. And that's where we then will shift over into the next space I want to talk about, which is X array. We're going to click on this one. So the main difference you can think about it conceptually between Pandas and X array is that X array has the ability to work with n-dimensional data, plus has the ability to add more metadata to your data values. They use different terminologies, which is good. It also helps with the web searching to figure things out. So we were talking about Pandas having data frames and series. So a Pandas object is a collection of series called a data frame. In X array, the larger object is called a data set, and then data sets are created of data arrays. Once again, the convention is to import X array as XR. And the first thing we're going to do here is we're just going to create a data array. So we've got NumPy A range, a 10,000 element range, A range. And then we're going to drop it into X array data array. And this is going to create an X array data array. And if we inspect it, once again, Jupyter loves playing with X array and it prints out very nice. You'll see it has our values, but it also has a lot more information. It has this idea of dimensionality with a name. So we have 10,000 elements with a name of dim0 because we didn't give it one. It has the values in here. It also has coordinates and attributes. So there's a lot more going on as far as metadata associated with this object. For example, yeah.
We have a question. What is 10_000? Why are you including the underscore there?
Yeah, good question. This is just a nice Python way of showing the commas, because that would be an error. That is the equivalent of the US comma for separating like the thousands, millions. So this is exactly the same. It's just a way to view that value easier.
Thanks, Ken. I will note we just have 2 more minutes here, so.
All right, I will try and get to the high points. So the point here is that we can then add metadata about our data. So here I've created a time array, which is going to have the name time. It has this idea of coordinates. So now I'm tying the data values to the coordinates. In this case is time. And you'll see that it's actually recognizing it as a date time 64. And then we can actually add attributes, which is going to be metadata about it. So we have long name and units and some other stuff. And the second part here is just the different syntax of how you would actually build it. Just to be quick here, I'm going to skip some of that just so you can understand what's going on here. But a data set is now a collection of data arrays. So now what I'm going to do is I'm going to create 2 2 Numpy arrays, 2 different data arrays, and then time is going to be my coordinate. And so what I'm going to do is I'm going to create 2, you'll see them here as data vars, 2 different data arrays. I'm going to tell it the coordinate, and I'm going to build up this idea of a data set. So now I have a collection of data arrays. So you have 2 of them here, and they are sharing the same name, the same dimension, and they're also sharing that same values exactly. So they're sharing the same coordinates. The nice thing about this is that it also collects it all in the same object, so you can pass around that object, and everything goes with it. So all the data values, the coordinates, all the variables, and the attributes. If you want to extract that one value, you just have to give it the name of the data array, and it extracts the entire data array. If you want the values, you want to do a thing called .values, and that extracts just the values from that data array. And then if you want to get one particular attribute, then you just do .attributes and the name of that particular attribute, and you get that attribute back out.
All right.
You want to stop there, Adam?
Yeah, I think that's a good stopping point, and I believe Max is maybe going to go into X Array a little bit more on Friday as well, right, Max?
Yeah, I was going to mention on Friday I'll be talking about X Array and sort of the Pangeo stack. So if people are interested in a deeper dive into X Array and that side of things, this is a really great introduction to it. But yeah, I'll be covering that more in depth on Friday if people are interested in that.
Yeah, no, this was great, Ken. I've been using Python for years, and I still have been learning a lot here with these tutorials. So, for those that have this up, feel free to keep going through this in your free time. It's a great resource. So,
yeah, thank you everybody for listening. It's hard to get through these 3 in such a short amount of time. So yeah, keep going by yourself.
Yeah, and Ken, thanks for presenting. This was a lot of great information. So